Hello everyone, I'm He Liu from Beijing Jiaotong University. Our paper is Learning Combinatorial Solver for Graph Matching. Learning-based or learning-free approaches to graph matching have been developed and explored for more than a decade. However, previous learning-based algorithms, with or without deep learning strategy, mainly focus on the learning of node and edge affinities generation, and pay less attention to the learning of the combinatorial solver. In this paper, we propose a fully trainable framework for graph matching, in which learning of affinities and solving for combinatorial optimization are not explicitly separated as in many previous arts. Specifically, we transform learning of graph matching to the problem of selecting reliable nodes from a constructed assignment graph. This figure illustrates a sampled assignment graph, where each candidate match between G1 and G2 corresponds to a node in the assignment graph GA. Thus, the original graph matching problem between G1 and G2 is converted to classifying the nodes in GA into positive nodes and negative ones. Our algorithm combines only geometric coordinates to form the initial attributes of the assignment graph. No appearance cues is used. The proposed learning pipeline for graph matching consists of 4 modules, including the assignment graph generation described before, and the encoder-decoder. The encoder module takes the contrasted assignment graph as input and transforms its attributes into latent representations. Decoder is coupled to the encoder module, which reads out the final output from the updated graph state and reports the predicted node labels for loss computation. Convolution Module is the core component of our learning framework, which convolves the information of neighborhoods of each node to form a structured representation through several convolutional operators. Each instance of the convolution module consists of an edge convolution layer and a node convolution layer. They are both consist of an aggregation function and an update function, where M is a parametric matrix. Both update functions are parameterized by MLPs. Finally, we adopt coarse entropy loss to compute a permutation loss, and use the auxiliary matrix B to evaluate the degree of satisfaction of the one-to-one matching constraints. We evaluate the proposed algorithm on 4 benchmarks in comparison with 8 state-of-the-art algorithms. The first benchmark is synthetic 2D point state set. As illustrated in this figure, our algorithm exhibits stronger robustness against both noise and outlier than compared baseline algorithms. In this figure, it's observed that the deep learning methods GMNPCA and ours are relatively robust against deformation and outlier by learning a more robust affinity function. In particular, our method outperforms all baseline methods in general and achieves about 95% matching accuracy under R-tested scenarios. The Velo object dataset is considered relatively easy because the lack of pose, scale, and illumination changes. Our method achieves the best matching results in all object classes except the dark class. The last benchmark is Pascal VLC keypoints dataset. As illustrated in this table, our algorithm outperforms not only non-learning baselines, but also all learn-based baselines.